Welcome back to the Journal Club, the classics of immunology. And before I forget, please go on the YouTube site and like this video and then click on the little bell to get notifications for more. And then also scroll down and go on to my website and check out, because all of the classic papers of immunology are there just for your viewing if you can't sleep in the middle of the night. And also the social media sites that I have. I'm quite active on Twitter as well as Instagram. So today's paper is one of the landmark papers that came out of my lab. The authors are Steve Gillis, Mary Firm, Winnie Wu, and Kendall Smith. And the title is The T-Cell Growth Factor, Parameters of Production and a Quantitative Microassay for Activity. And this is where we coined the name or the phrase T-cell growth factor. That had not been one of the T-cell derived factors until this paper was published. Came out in the Journal of Immunology in 1978, June of 1978. To give you a little background on the authors here, and of course, we talked about Steve Gillis, who was just a beginning graduate student in the lab at Dartmouth College in the biology department. Mary Firm was the first technician that I hired, and she was a sterling person. She was a Phi Beta Kappa graduate of Oberlin College, and I always had a soft spot in my heart for Oberlin College, was in the north of Ohio. My father had graduated there also as a Phi Beta Kappa, that my mother continuously and constantly reminded me that he was a Phi Beta Kappa. And so what are you going to do about things, Kendall? Anyway, I hired Mary when I first was funded from my first grant in 1975. And so this was 3 years later. Then Winnie Wu was a Dartmouth Medical School third-year medical student. She was just performing a 3 or 4 month stagiaire with us. And this was just the fourth year of the lab, essentially. So we'd started in 1974, and this is 1978 when this was published. This was a group effort. I mean, everybody was involved in all of the experiments that I'm going to talk about soon. And I elected to put the authorship with Steve Gillis first, and then Mary Firm and Winnie Wu, and then myself last, because I felt that Steve had, although he didn't contribute any more than anybody else, he had the most to gain from this whole thing, because he was a grad student and his career was going to be in the biz. And so that's why I arrived at the authorship of this paper. But it could have been anybody as first author. So in the introduction, what I don't say in the introduction is the first thing, and that is because of what we just reviewed last week in terms of the long-term culture of cytotoxic T cells, we found ourselves in the sort of the production mode of making conditioned medium in order to keep ourselves alive. And I was so concerned that we were going to lose our cells, our long-term cultured cells. So we passed them every day, 7 days a week. I would come in on the weekend, Saturday and Sunday, and pass the cells. So we always had in the incubator cells that had just been passed, cells that had been passed yesterday, and cells that had been passed the day before yesterday. And we just kept that going, and we kept that going for years, more than a decade that way. We froze them down as well, and we could recover them from a frozen sample. But even so, I didn't want to lose the cells that were growing. And I wanted to keep them growing to see how long they would grow, essentially. So we were in the conditioned medium production mode, and after a while, that became a big deal. We migrated from mouse conditioned medium, mouse splenocytes, to rat splenocytes, because the rat spleen was about 5 times bigger than a mouse spleen, and we could get therefore more milliliters of conditioned medium from a rat spleen. And then what we found was, as we were just trying to keep these cells growing, is that there was variation from batch to batch of the conditioned medium. Some seemed to be better than others. The cells, they didn't look so happy, and they weren't growing quite as fast, and so forth. So we knew that we needed to standardize this whole business in some way. And in order to do that, we knew that we needed a quantitative assay for this, whatever this was, what we named and coined the term for T-cell growth factor. But that was just a name. It didn't have any molecular connotation to it at that time. But we needed a way to quantify from batch to batch to batch to batch so that we could standardize it. And so we didn't have to worry about how much growth factor was in one batch versus another. We also figured that we could then, if we had a quantitative assay, we could determine the best time to harvest the supernatant after we established the cultures, and we could find out also whether how long the growth factor activity lasts in a conditioned medium. And the materials and methods of this paper, in order to produce the conditioned medium, we tested several different T cell mitogens, concanavalin A, PHA, of which were T cell mitogens specific, and lipopolysaccharide, which is a B cell specific mitogen for both mouse and rat spleen cells, and also pokeweed mitogen, which would activate human cells, both T cells as well as B cells. We put the cells into culture at 1 million cells per ml and RPMI 1640 medium with 10% fetal calf serum. And then we could assay several time periods after that to find and to harvest the supernatants. And what we would do then, when we would spin down the cells in a centrifuge, and we would take the supernatant off, we would filter it through a millipore filter and store the conditioned medium at 4 degrees in the refrigerator. We didn't freeze it because we didn't know whether or not freezing was good or bad for the whole thing. We tested several different mouse strains, C57 Black 6, the DBA2 strain, and also the BALB-C strain. And we used, when we used rat spleen cells, we used outbred rats from Charles River. We also tested human cells, human peripheral blood mononuclear cells, PBMCs. And for those, we stimulated them with PHA because we already knew that PHA was the best T cell mitogen in the human. So that was the TCGF production. And everybody in the lab did this. I organized the lab so that everybody, there were never a dull moment. If you didn't have anything else to do, you could make conditioned media, So for the TCGF assay, for that, we used our CTLL cells, our cytotoxic T lymphocyte lines, number 1 and number 2, because they were continuously growing in conditioned media. And what we would do is we'd harvest them from one of these cultures and we would spin them down. We would wash them with changing media and so forth. And we would then seed those cells at a very low cell density, 5,000 cells per ml. And we put them in their special growth medium, CLIX medium, with 2% fetal calf serum. In order to do the assay, we would put them in 96 well microtiter plates so that we would put 100 microliters of medium in all of the wells. And then we would add our sample into the first well, another 100 microliters, so that we would then have 200 microliters. And then we would do what we call doubling dilution. So we passed 100 microliters from the 200 into the second well. And so then we would bring them up and down, up and down, up and down with the pipetter 5 times. We always did it exactly the same way. And then we would then pass it down the line that way, making these doubling dilutions or log to the base 2 dilutions. We use these 96 well microtiter plates that several different companies manufactured that would hold a maximum of about 0.25 microliters, or 0.2 anyway, 0.25 microliters. After we diluted out our sample, and we always had a standard, which we put in every assay, we would then add the cells also in 100 microliters so that the total volume was 200 microliters. We put those plates in the incubator, humidified 37 degrees, and culture them overnight. And then the next morning we'd come in and add tritiated thymidine, 50 microliters to each well. So then at the end of an overnight incubation period, we add the thymidine to each of the wells, 50 microliters, and then wait for 4 hours, and then harvest the whole microtiter plate onto an automatic harvester machine, which then sucks out the fluids and puts them onto glass fiber filter paper that then we can then put in tiny little vials and add scintillation fluid and count them in a liquid scintillation counter. And this assay that with the doubling dilutions and the target cells and so forth, it's basically just a copy of the erythropoietin assay that I had worked out when I was on a postdoc over in France when I was working on erythropoietin. And the only difference was, so we did the same thing, except we had EPO samples that we would dilute out. And then we would add mouse fetal liver cells that were enriched for erythroid precursor cells. And then we'd wait overnight, and then we would pulse them with thymidine. And we would get, as a result, which is I'm going to show you now in figure 1 in screen sharing. So figure 1 is a plot of tritiated thymidine incorporation into the CTLL cells on the y-axis, and on the x-axis is the percent of factor sample, starting to the left at 100%, then 50%, and so forth, as we do the doubling dilutions down the line. And the open circles is our control standard TCGF sample, and in the triangles is you see the same thing that's been passed through a cephocryl column, which would remove all of the concanavalin A, because of the fact that concanavalin A is itself a mitogen. The question was, well, maybe it's the concanavalin A in the conditioned medium that's causing these cells to grow. And so this was an attempt on our part to remove the con A and then retiter the sample, and we got exactly the same thing. So without the con A in the sample. And then on the bottom here in the open squares is just con A added to fresh media. And of course, that is negative across the board. And so the other thing about these tritiated thymidine incorporations of this sample is that, in fact, if you look down the microscope in this microtiter well at all of these samples, the cells were absolutely dead and disintegrated. So without T cell growth factor activity, the cells don't last 24 hours. So the second figure number 2, is the quantification of T cell growth factor and the assay that we set up in order to find out how much factor activity we have in each sample. And so in order to do that, we arbitrarily made dilutions from here of a sample, and we diluted it in half and in half again, and so forth and so on. And then each of those samples became A, B, C, D, and E, and then we titered them into the TCGF assay. And you can see you get a whole series of parallel dose response curves. And for the most part, it looks like each time we cut it in half, we got half as much back again. And it's difficult in the raw data to really be confident that you're applying equal kinds of weight to all of the data points. And so we took advantage of the assay that I had learned on how the virologists titer their interferon assays. And what they do is they use what they call probit analysis or probability analysis. And there's a special paper that you use that then what you do is you take the maximal activity and you then calculate each data point as a percent of the maximal activity, and you plot it on this paper that is shown in the figure B, 2B, as a percent of the maximal activity. And you can see that this dilution curve here basically translates over to this dilution here, and you get a very much better straight line in that whole thing. And the reason being is that the probability paper, you can see that the distance between 50% and 60% here is smaller than it is between 80 and 90%. And at the other end, it's the same sort of thing between 10 and 20 and so forth, which takes the sigmoid dose response curve that we saw on the last plot and gets rid of the variability at both ends of the curve at the top end and also at the bottom end. So you can get these very nice plots, and then you can compare. You can say, well, okay, well, let's take look at the 50% point, and you can go along and compare how much factor activity you've got in this sample versus this sample. So that's how the whole probit analysis works, and that was good. That was critical. Then, if we wanted to give it some sort of a quantitative number to these dilution curves, we basically just arbitrarily said that, okay, our control standard sample has a value of 1 unit per ml, and that diluted out to be a dilution of 1 to 10. And then the next one over then had a dilution of 1 to 5, and that gave 50% of that activity, or 0.5 units per ml, and 2.7 instead of 0.25, and so forth. And so this units per ml of T cell growth factor activity has, to my dismay, actually persisted until the present time, until 2021 from 1978. Along the way, and I'll get into it as we go on in the journal club, we actually could ultimately calculate the protein concentration of purified TCGF activity as a consequence of these assays, so that we could give the concentrations in either nanograms per ml or molar concentrations, which is much better, particularly when you get into the calculations of the affinity of the cellular receptor for IL-2. But that's getting ahead of myself again. So then in figure 3, what we did an experiment, because we were just sort of arbitrarily harvesting our supernatants at 48 hours after the initiation of the production cultures, rat spleen cells usually. But we didn't know whether that was some maximal, the best time to harvest. And so we did this experiment here. This is just one example of it, where we put the cells into culture, and then at 6 hours, 8 hours, 10 hours, and so forth, we took some supernatant out to measure for the TCGF activity using our quantitative assay. And you can see that what happens is that in this particular experiment, the peak activity was at 48 hours. And okay, that's good. And we sometimes it was at 24 hours, but for the most part, it was either 24 to 48 hours. And then we sort of hoped that was true. But then this is what we didn't anticipate. If we let it go for 3 days, 72 hours, it had fallen off by more than 50%. And then by 96 hours, 4 days, it was essentially zero. And so we looked at that and we said, well, that's interesting. That's why the cells are dying when they don't have enough T cell growth factor. And so, because we hypothesized then that the reason it dropped off like this was either because the cells had secreted a TCGF specific inhibitor kind of thing, which we were sort of looking for anyway, or the cells actually consumed the growth factor. And as they got to a higher cell density, they used it all up. And in order to do that, we did the experiments shown in figure 4, where we took the standard growth factor sample, diluted it in half with fresh medium, or we diluted it in half with 96-hour conditioned medium. And you can see that if it was really an inhibitor in here, it should have destroyed the activity altogether. And it didn't do that. It just diluted it in half. So we knew that what was going on, or at least we could hypothesize on the basis of these data, that the cells, when they got to a higher and higher density, that they would consume the IL-2, or the TCGF. So on the basis of that experiment, then we decided that, well, if we could take our CTLL cells and we could seed those into culture at a very low cell density, here at 5,000 cells per ml, and we could give them a maximal amount of what we called 1 unit per ml of TCGF activity. And then every day we could take a sample out and count the cells, and also take the supernatant and put it into our quantitative assay. And you can see that the TCGF activity just sort of gradually went down as the number or the density of cells grew up. And then if we left those cells here at day 8 of culture, 192 hours, without any TCGF, the next day we came in and the cells were dead. So that told us really what we needed to know, gave us the parameters, and really shows the power of this quantitative assay in order to be able to understand how to make this stuff so that we could grow our cells. We also wondered whether or not there was any correlation between the mitogen-induced thymidine incorporation of the producer cells, the rat spleen cells, and the production of the growth factor. And you can see as we titered Con-A with these rat spleen cells, the stimulation index of the thymidine incorporation occurred about the maximal about 5 micrograms per ml. And then you can also see the units of activity coming out exactly the same thing. So that the mitogenicity of the Con-A correlated just exactly with the amount of growth factor produced. So that being said, we sort of felt that the T cells were making this, which is one of the reasons that we called it T cell growth factor, but we hadn't shown that, we hadn't proved that. So this table 2 shows data from experiments where we looked at the comparison of the different kinds of mitogens and also different cell sources to make this growth factor. We took normal mouse spleen activated with Con-A, we got a unit per ml. If we treated the spleen cells with anti-theta serum plus complement, we would reduce it. It only reduced it by 70% essentially in this particular experiment. If in complement alone without the anti-theta didn't do anything. Then normal mouse serum plus rabbit complement didn't do anything. So, and then we looked at mouse spleen activated with PHA, with LPS, and LPS, which is a B cell mitogen, didn't make any TCGF. Pokeweed mitogen did. MLCs in both instances here did. And then we tried fibroblast conditioned medium, and that was negative. We looked at rat spleen cells with Con-A, PHA were positive. LPS was negative. Pokeweed mitogen was positive. And human peripheral blood activated with PHA was positive. So that's the end of the screen sharing. And that's the end of the results section of this paper. In the discussion, get to my notes here for the discussion. We make the following points. We say, number 1, this is a sensitive assay. It's reproducible and it's quantitative. And it's a microassay. We don't need a lot of supernatant to test this. We only need a couple hundred microliters. And it's rapid, and that was very important. It only takes 24 hours for us to turn around and get all of the data. So that means, and because it's micro, we could do multiple samples. We could do as many as we wanted, as many as we had target cells for, essentially. And we thought that this was probably the origin of the T cell growth factor was a T cell, because only T cell mitogens, LPS, didn't make the growth factor. And anti-theta sera plus complement would markedly reduce the amount of factor produced. And in the discussion of this paper, we mentioned that, there's been a bunch of other factors that have been talked about in the literature, beginning with blastogenic factor from 1965. And we've gone through these papers in the journal club. And then they were several papers right around the time of this paper in 78 of a factor activity that was thought to be derived from allergenic lymphocytes. And so it was called allergenic effect factor. There was also, as you know, there was lymphocyte activating factor that had been defined pretty well, that it was not coming from a T cell, but it was coming from a macrophage. And it would cause T cells to proliferate. And then there was T cell replacing factor that would replace T cells, the T cell requirement to make antibody for antibody forming cells coming out of plasma cells. There was xenogenic effect factor. There was a CTL helper or replacing factor for the generation of cytotoxic T lymphocytes. And all those had been described previously, but what they were, nobody knew. I mean, they could have all been the same thing, or they could have all been different factors that had mitogenic activity for T cells. So the fact that lymphocyte activating factor would cause the cells, other thymocytes was the regular assay, if you recall. That immediately set us off on, well, we've got to figure, and one of the reviewers of this paper said, you know, how do you know this isn't LAF? That's when we decided that LAF was a joke. And so we also then stated at the end of the discussion of this paper that this microassay will help us to isolate, purify, characterize, and identify this T cell growth factor at the molecular level. That was very, very important. So that was it for this paper. And it turns out that subsequently what happened with this paper is that it became the paper that everybody else used to assay for their favorite growth factor or their favorite factor, particularly the quantitative aspect of this thing. And it ended up, after a couple of 3 decades, as the second most cited paper in the first 100 years of the Journal of Immunology. I thought that was pretty cool. And also, it was the most cited, it has been the most cited of any of them or all my papers, which isn't surprising since it was the most cited anyway. And I think the thing about this paper is that one of the criticisms we had from different people was that we put too much data in our papers. What kind of a criticism is that? I'm very proud of this paper because I think it really illustrates careful and meticulous science and how to go about things. And it really illustrated the power of quantification, in which I've mentioned before that Sir Peter Medawar back in the 50s emphasized that you really need to quantify things in biology in order to really move ahead and to make conclusions about things and then therefore formulate new hypotheses. And this paper allowed us then to proceed to the next steps that we'll talk about in the Journal Club as time goes on. So if you like this journal or this Journal Club, like it on YouTube and click on the bell and check out my website, look on the writing tab at the top, and you'll get all of the famous papers in immunology, and then check out all the videos or all the social media, in particular, Twitter and Instagram. Thank you very much.